If you remember last time we were doing the chain rule, chain rule is in section 14.5. My goal today is to finish off chain rule. So let's get into some practice. Kind of overlap one. This one's not unlike question 6. It's changed enough so that you have your own version of it to still do. Z is equal to these two things multiplied together. R is a function of S and T, and theta is a function also of S and T. And in this question, you're going to be asked to find the partial derivative of Z with respect to S and the partial derivative of Z with respect to T. I'll pick one. I'm going to do the partial derivative with respect to S. Excuse me. So the formula for that is dz dr times dr ds plus dz d theta ds. Now there are lots of different flavors of the chain rule, and you're going to see today more complicated versions of that. But there are a couple of things that kind of strike me as, have you noticed that if you want, say, dz by ds, that if you take the pieces, don't these drs kind of cancel out and you get a dz ds out of it? And don't these d thetas cancel out and you get a dz by ds? Did you notice that kind of shape? It's not really that they cancel, but in a kind of visual way they do. Yeah, that kind of helps me to remember if I've got the formula correct, because you have to create this formula for this particular situation, right? So what we're now entering into is just the partial derivative stuff. So if you differentiate this guy with respect to R, nothing very interesting happens. Would you agree that the derivative is actually the same guy? Now, if you differentiate R with respect to S, so we're up here now, well, the S disappears and you get left with a T. Plus. Now, if you differentiate Z with respect to theta, you get e to the r cosine theta, and you multiply that by the derivative of this. And this is not pretty, because I really have to do a little bit of engineering on it. Would you agree to differentiate the square root of s squared plus t squared? You have to write it as a fractional power. And by the way, do you notice that this derivative with respect to, in this case, s, isn't that going to be a chain rule, i.e. a calc 1 chain rule, right? A power rule stroke chain rule. So you multiply by the power, you reduce the power by 1, and then you finish with the derivative of what's inside with respect to s, which gets me to s. Now, we're finished as far as the derivatives are concerned. All I'm going to do now is some style point stuff. For the first term, I'm just rearranging the order. The 2.5 cancel, that belongs downstairs. So what I'm going to get is plus s e to the r cosine theta all over s squared plus t squared to the half. And being a kind of purist, oops, that's going to go there. One of the rules of style points is that the answer should look similar to the original. Are we comfortable with that question? Does it seem you can follow the process? Right. I was having a conversation earlier with one of the students, one of our students, and we were talking about WebAssign is sometimes not very, it is pernickety. And so it might take this answer with a negative a half power, but it won't take the answer if you write it as a fraction, or the other way round. It might take the answer with a half power, but won't take it with the square root. Or it might not take the half power and you need the square root. In other words, you may have the correct answer, but you may not be writing it in the form that WebAssign wanted to see it so that it can check it. So when you get that little dreaded red X, it doesn't really always mean I'm wrong. Couldn't it just mean I've not written it in a way that WebAssign was hoping to see it? And that would be fine if WebAssign was consistent and kind of followed like the usual rules of algebra and style points, but it isn't always consistent. And one of them was telling us, if she doesn't mind me sharing, there was like a question where if you put in a decimal, it was fine. And then the next question, you had to put in 3/4 because it didn't want you to see a decimal there, right? That's just a small example of that issue. So I'm just giving you a kind of heads up here. If you're comfortable that the answer's correct, you may have to tweak it a little bit, you know, make it look like this or make it look like that, or whatever, just to make it happy. And I think if you do practice another example or something, she was saying, you can actually see the format of a similar question, and then you'll say, oh, they've got a square root in their answer, I better make a square root in mine. Or, oh, they've got a half power in their answer, I'll make mine with a half power now. And that might give you a little bit of a clue of the form that an answer is. Now, in normal human being world, it wouldn't be an issue. Wouldn't I be able to just look at it and say, yeah, you're right, I can tell they're the same thing, no biggie, right? But in WebAssign, it doesn't always work that way. So let's up the ante. Let's do Z is equal to x squared y plus the tan of xy. And let's make x p plus q plus r. And let's make y p squared plus q squared plus r squared. Whoa, look at this. Z is a function of two variables, x and y. But each of these two variables are themselves functions of three other variables, p, q, and r. Right, so that's a little bit different, right? Still chain rule, right? But it's a two variable main function having three variable subgroup going on. And I want to find the partial derivative dz by dp. So far, right? So we need to create what the formula for that might look like. Okay. Okay, well, that's not much of a start. Anybody want to start the formula off for me? So dz by d what?
By dx
times
dx over dp
plus
dz over dy times dy over dp.
We all comfortable with that? Right. Now, we're going to finish this question off, but once I finish it off, I'm then going to show you another flavor, which gets even harder. Right. So if you differentiate this with respect to x, you get 2xy. Uh-oh. I want to differentiate the tan of xy. So basically that's a like calc 1 chain rule situation, right? It's a tan of something, right? What's the derivative of a tan?
Secant square.
Okay, so it's going to be the secant squared of xy times the derivative, partial derivative of xy with respect to x. Can you see where that extra y came from? Right. Followed by the easy bit. dx by dp is just 1. Now, if you go the other way, dz by dy, in this case, you'll get an x squared. When you differentiate the tan of xy with respect to y, you'll get another secant squared xy times the derivative of xy with respect to y, which gives you an x. And then you finish off with the derivative of y with respect to p, which is 2p. And all I'm doing in this line is some very minor style points. Yeah. There we go. Yeah. I guess I could take it a little bit further. I don't know whether this version or that version is what WebAssign was looking for. Maybe it'll take both. That's possible. But you know, the usual, what does it want? It's hard to tell. Now, you know I make mistakes. So if I forget a 2 somewhere, or that should be 2x squared, not 2x, fix that yourself. You can tell me. Now, let's do w, a new variable, and it's x plus y squared plus xyz. And x is p plus r, y is p take away r, and z is pr. So w is a function of 3 variables, x, y, and z. X, y, and z are in turn functions of 2 variables, p and r. And in this question, let's go looking for that one. I'm going to just put a little mute on you because I'm getting some feedback here. It's very distracting to hear your own voice when you're saying things like a little echo. Come on, you can do it. There you go. Now, 3 variables followed by 2. To do dw by dy, right, that partial derivative, not by dy, my apologies. You're always being asked to find the partial derivative in terms of one of these guys, right? Now, to get that guy, use x, use y, use z. And do the x with a p. Then do it with a y. And then do it with a z. Do you see how this version ended up having 3 pieces, whereas this version only had 2? Do you see how the chain rule formula has to adapt to how many variables in the primary function and how many variables in the secondary functions? Here there was 2 variables in the primary and 3 variables in the secondary. Here there were 3 variables in the primary function, but each of those has only got 2. Are we comfortable with that version of the chain rule? Because you need to have this guy to get the right answer, don't you? You need to know what of the many permutations out there could happen. Right, now this hopefully will go smoothly. That guy's 1. If you differentiate this with respect to p, you get 1. This guy here is, no, it's not. I forgot. Let's do that again. It's 1 plus yz. There we go. Now I can do it times 1. The middle guy is 2y plus xz. And then I can differentiate this guy with respect to p, which is also 1. And then the last one, nothing, nothing, you get xy, and you differentiate this fellow with respect to p, you get r. So it looks like we're going to get 1 plus yz plus 2y plus xz plus xyr. Yeah. Can't really do much more with that. Are we okay with that permutation? Any questions about it? Are we good? Let's add 1 level to that. Same question. You're being asked to find that partial derivative, but at that point. So what does that mean we need to do? Well, if p is 1 and r is 2, great, then won't x be p plus r, which is 3? Won't y be p take away r, which is -1? And won't z be p times r, which is 2? So although I was only told those two, don't I really know everybody? So I then say, okay, 1 plus y times z plus 2y plus x times z plus x times y times r. And that's 1, take away 2, add 6, take away 6. And I believe in this case the answer is -3. So can you imagine in some of the partial derivative chain rule questions, not only are you going to find the partial derivative, you might also have to evaluate it at a given value for p and r. Any questions? Are we good? If we are good, I'm going to move over then, and we'll look at what some of the homework questions look like. And as we go through them, if a question looks weird to you, we can pause and maybe, if not do it, at least start it. Are you looking at my screen too, which says question 7? Yeah, I got a nod, good. Okay, hopefully it's big enough for you to see how to do it. Can you see it's basically z is a function of 2 variables and each of these is in turn a 2 variable, right? So that would be 2 primary, 2 secondary. Just differentiate the usual way. 2 primary, 2 secondary with a tangent. Okay. Be a little bit careful when you differentiate tan of u over v, because won't it be the secant squared of u over v times the derivative of u over v? And when you're doing a u, that's easy, it's 1 over v. But when you do it with respect to v, isn't u over v a little bit messier? It ends up being negative u over v squared, but you have to work on it. So be careful with that. Here we have w in terms of x, y, and z, and x and y are in terms of two variables. So this would be 3 primary variables and 2 secondary variables. Can you imagine what the chain rule formula for that particular circumstance would be? And there's the two guys that you're going to be finding. What's this one? This is 3 primary and 2 secondary. Okay. Oh, and do it when x and y. So plug in the numbers when you're finished. So your answers here won't be the algebra. The answers here will be like 12, you know, and whatever, -9, right? It'll be numbers. Because you will find the partial derivative, and then you will make x 0 and y 6, which means you'll then be able to find u, v, and w as numbers. And then you take your partial derivative like I did a few moments ago, and you plug in all the x, y, z's, u's, and v's, and w's, and calculate, hopefully, relatively quickly, a nice answer. Is there any of those guys that we've gone through that you want me to do a little bit more on, or do you feel comfortable about tackling them? No issues? Okay. N is an ugly fraction. So it's 2 primary variables, P and, no, it's 3 actually, P, Q, and R. And each of these is a 3 variables. So there are 3 primary variables, P, Q, and R, and 3 secondary variables, U, V, and W. So isn't that a 3 by 3? Do you feel comfortable about what the chain rule for that one would look like? You are allowed to say, could we see the formula? Or I'm not 100% sure.
Can you see the formula?
Okay, good. Now, we don't need to do the specifics for the formula. I just need to show you what the formula is, and then you can plug in the details later. So what we're looking at here is 3 primary variables, right? So the variable n happens to be P add Q over P add R. In other words, there's 3 variables, right? P, Q, and R. And then P, Q, and R are in terms of U, V, and W. So we are being asked to find the partial derivative of n with respect to one of these guys. Well, it's dn, dp, dp, du. So you see that little cancel, you get a dn by du, and then you do the partial derivative with respect to q, and then you do the partial derivative with respect to r. There is a kind of structure to these formulas. Can you see the little cancel me out? And what you're left with is 3 versions. Essentially, this piece here is the contribution to your answer caused by P. The middle bit is the contribution of your answer, the bit of your answer that's contributed with the Q. And this one is the piece of the whole answer that is contributed by the R variable. Theoretically, couldn't you do a function with 10 primary variables and 7 secondary variables? I mean, the thing would look like 5 feet long, but you could do it, theoretically. Now, I'm going to show you a little piece of information from Calc 1. you remember in Calc 1 a technique called implicit differentiation, where you had to find dy by dx, right, the derivative of an implicit function? That's basically a curve that has x's and y's mixed up. These curves can be quite weird. Aren't they allowed to loop on themselves and do all sorts of stuff that a function can't do, right? You recollect these questions from way back in the day? Can you also recollect how ugly they were to do? How messy they were? And all the lines that you had to do. Because essentially, don't you have to differentiate each of these separately with respect to x? And then you have to solve for dy by dx, which very often involves 3 or 4 lines of moving things around and distributing things and taking out common factors and subtracting stuff and dividing stuff and who knows what else. Okay. So here is an equation. Dy by dx is equal to the negative of the partial derivative of f with respect to x over the partial derivative of f with respect to y. So your Calc 1 derivative can be found by using partial derivatives. So you might say, well, what's this f they're talking about? Well, what you do is you take your implicit equation that might be written like this, and you rewrite it with everything on the left-hand side. And this guy is your f, technically. It's a function of x and y. Now, if I find the partial derivative with respect to x, I get 2x, I get y squared, I don't get anything, and I get minus 1. If I do the partial derivative with respect to y, I get nothing, I get 2xy, I get negative cosine y, and I stick a negative in front of it. Just put my equals here. And there is my answer. Did you see how quickly I managed to find the partial derivative of a really ugly implicit function? Isn't that kind of cool? That you can find dy by dx, the good old Calc 1 dy by dx, by just using this formula here. Partial derivative of everybody with respect to x divided by the partial derivative of everybody divided with respect to y, and stick a negative in front of it.
Is this true for all functions?
For all 2 variable functions, right? So by that I mean y's and x's all jumbled up.
Okay.
Oh, that's still pretty cool, isn't it?
Yes.
Yeah. I don't know if it's crossed your mind, but you might be thinking, see, when we were doing Calc 1, why didn't you just tell us this? Instead of getting us to do 12, 20 minutes, whatever it took you. Can you imagine how big some of those guys were? Weren't they really messy and really big? And isn't it now like a 30-second question if you're careful? I think the reason, well, I don't think, I'm pretty sure I know the reason. You ever heard that saying, a little knowledge is a dangerous thing? If we told you this, wouldn't we have to tell you about a thing called partial differentiation? Right, you'd have to understand that. And the danger is that if you know about partial differentiation, wouldn't you start using all the way over Calc 1 stuff in lots of places where you shouldn't be doing it? Can you imagine that might happen? And so it might make this question very easy, but might it also at the same time screw up all your other Calc 1 stuff. Right? And so it's just, there are lots of little cool things that we don't tell you that you haven't found out yet. So it's like a little secret that you've now been, the door has been opened and we've allowed you to have a look in. I still think that's a fascinating result. But then again, maybe I'm just easily fascinated. I think it's kind of cool. Right, let's do another one of this, because there are some questions in the homework that get us to use it. I think they say, use this equation, and then they give you one. So what one am I staring at right now? Oh, I'm staring at one that's like 12. So how about 9x squared cosine y equals x cubed plus y cubed, right? I'm just mucking about with it, so I'm not doing 12, it's just like 12. Okay, in order for us to use this formula, don't we have to do just a little bit of tidying up algebraically? And the tidying up is everything equals 0, right? That's what you do. So in this case, 9x squared cosine y, take away a y cubed and an x cubed equals 0. And this guy is our f. So we're being asked to find the good old-fashioned Calc 1 dy by dx. It's going to be negative. I'm going to use that notation as well. Isn't that the same as this? Right, just different notation. Right. Big fraction. Partial derivative of this guy with respect to x. 18x cosine y, take away 3x squared. On the bottom, partial derivative of this, but with respect to y. Well, if you differentiate a cosine, you get a negative sign, so that's why that negative is there. Nothing for that. Negative 3y squared. And there is your answer with a negative outside it. If you don't like the negative outside, you could give it to the top. If you give it to the top, the answer looks like this. If you don't like this negative, you could give it to the bottom. If you did, the top would be unchanged, but the bottom would receive a new negative. And maybe this is just me, but you know, out of all the choices, style points wise, I like that third one. Why do you think I like that third one?
No real negatives. They have to multiply out.
Yeah, it just looks prettier. Now, it's hard to say what makes things look pretty, because mathematics, to me, that looks pretty, right? Now, which one of those three answers is the one that Webb assigned? Hopefully all three, because they're all correct. But maybe only 2 out of 3. And you know Murphy's Law, the one that you use is the one that didn't like. And if it's really being clunky, maybe only one of those 3 it will understand. But bear in mind, you are correct. So if you do 3 shots at a question and you get 3 crosses, and then you oh God, I'm right, you know, then you do the usual. You shoot me an email saying, look, this is what I got. This is the answer. Give me the points. And provided you're correct, I will give you the points. All right. Has anybody had many issues with WebAssign? Or am I flogging a dead horse here? It's going pretty good, Eleanor? Yeah, okay. Well, that is nice to know. Can I pause a second? Okay. Now, we get somebody called MATLAB. Who are you?
Oh, sorry. It's Lindsay.
Lindsay, we need a couple of things from you. The first thing is, will you log on as Lindsay? Because when I take attendance, I don't know who MathLab is. Perfect. And if you can get your video to work, that would be great as well. Thank you. Yay. Are you doing MathLab and some other thing and that's why you're doing it?
I tutor at Peninsula College's math lab.
Oh, as your kind of sign-in name?
Yeah, so sometimes I turn up in meetings like that, and then I just have to remember to change my display name.
Okay. You're lucky it wasn't anything like Bouncing Rabbit or something. I get some weird emails from students. Yeah.
Yeah, nothing like that. Just a tutoring job at a different college.
Well, that's cool because it keeps your math skills up.
Yeah, it's actually great. It's like constantly reviewing.
Right. Did you do were you here, I think you came in a little bit later, were you here for the Y by DX trick that we showed everyone?
The meeting link, when I clicked it, gave me this weird message. And it said invalid meeting ID -1. And then today's message did not give the Zoom meeting password. So I was there for a bit like, what do I do? And then a friend suggested like, well, try the other meeting ID and password that he sent in the other message. And for some reason that had not occurred to me. And I did that and then turned up. But I will watch the video later today.
Okay. It was just I was going to say to you, please don't tell your Calc 1 that.
I won't.
Right. Just keep that as a secret. But you can use that to know what the answer is yourself before you do it the way Calc 1 has to be done. So it's nice if you know where you should end up. It's just that we're taking the elevator and they still have to use the stairs, right?
Yeah.
That's my analogy right now. So let's return. Where am I going here? Let's return to a second surprise or shortcut or whatever the darn thing is. I'm trying to find the name of it. Can never find things when I want them. Okay, where are you hiding? No, done that. I may have actually done. There was another question I'm sure I wanted to do. Oh, here it is. And this one is going to be like question 13. And the function I'm going to do it to is e to the z, and it's going to be x, y, z squared. And we're being asked to find the partial derivative of z with respect to x. And you're going to say, but this isn't a chain rule, because in a chain rule, x would be p plus q, and you'd have a secondary variable. And you're right, it's not a chain rule in that sense. In fact, isn't this implicit partial differentiation? And I could do this question the Calc 1 way. Remember the Calc 1 way? E to the z, dz by dx, followed by some kind of product rule, followed by moving things around and all that cool stuff. Or I could do this. I could use that formula. Now, do you notice that when you're doing dz by dx, the z goes in the bottom and the x goes in the top? It's exactly the same formula if I have that guy. I can't find it now. Do you know the dy by dx one that we had? There it is. Did you notice the y goes in the bottom and the x goes in the top, right? Now, remember the process. So let's take you through it. You make everybody on the left-hand side. And this here becomes our f. And so to do the partial derivative of z with respect to x, stick a negative, and you do the derivative of this, the partial derivative of this with respect to x, just good old-fashioned x, not implicit differentiation x. In other words, don't care what you are, you're 0, and this guy gets you a negative yz squared. And then you do it with respect to z, and this guy gets you an e to the z, and this guy gets you negative 2xyz. Now, did you notice that I differentiated all of this in the usual simplistic partial differentiation, which is there's only one guy that's a variable and everything else is treated like a constant. So we actually changed the way that we look at that expression. If I left it like this and did it yesterday's method, wouldn't that be called e to the z dz by dx? But now in this new technique, when you do this to it, each of these variables is considered independent of each other. So the partial derivatives are simply one guy's a variable and every other letter is considered not. Now, would you agree with a little tidying up, I'd probably give it to the top in this case. Wasn't that a lot quicker to do than how you would have had to have done it yesterday? So we didn't make you suffer quite as long as the other one. Didn't you have to suffer Calc 1, Calc 2, Calc 3, and then in Calc 4 we told you how to do dy by dx? You only suffered for one day. Yesterday we showed you the long way of doing this, and today we've shown you the shortcut way, which means you can choose whichever of those two methods suits you best. And me personally, I would jump for that one, right?
I have a question. So looking at the homework,
Yes.
some of the problems have like tables, and it says suppose f is a derivatable function.
Yeah, I just took those questions out. They're no longer there.
Oh, you did take them out today?
Yeah.
Okay, because they were there last night when I was starting to work on
They
the
were.
homework.
Okay. They weren't biggies. In fact, they were. I think two reasons. One is they were just awkward. I didn't like them when I thought about it. I thought, it's not really derivatives. You're just playing about with numbers. And the second one is that it doesn't. To me, it didn't give you any insight into the process because.
Okay.
It was just a side issue, so I thought, to heck with it, why bother? Are we cool with this, guys?
Yeah.
Yeah. So we are. Oops. My dog is. I don't know if you can hear her. Yeah. You wouldn't believe she's very ill with that barking, but poor old dear is very ill. Okay. Last question. I am about to go into uncharted territory. I am not an engineer or an electrical engineer, and to be honest, I'm not that interested in engineering stuff. To me, the most interesting mathematics is the algebra math, or the math that nobody has found any practical use for. They're just more interesting to me. But for the rest of you, here is partial derivatives. So hopefully you're looking at question 14 here, our last question for today. And the voltage V in a simple electric circuit is slowly decreasing as the battery wears out. Okay. The resistance R is slowly increasing as the resistor heats up. Okay. Use Ohm's law, which I did know. V equals IR. to find how the current is changing. At the moment, R is 300 ohms, I is that number, dV by dt is this guy, and dR by dt is that guy. So you have just been asked to find the partial derivative of I, let's see, with respect to t. And, oh God, time. Right. I'm not going to get this done. Okay, that's fine. I can do it tomorrow. Okay, will you all say hi so we get attendance done? Okay, there's a whole load of stuff I haven't written down here. How are we going to get the I by dt out of this formula? That's where we're going to look at tomorrow. But if I rearrange it, can't I do that? For instance. And if you look at it from that respect, won't that guy be di, dr, dr dt plus di, dv, dv dt? Agreed? And I'll find all these guys in terms of IR. Then we will replace, well, actually, I'll only be replacing these two with numbers and these two with variables, and then they get replaced by numbers. So, Remind me tomorrow to do that question in completion, right? But it's time up by my watch. I'm going to hang about because office hour is going to start directly after this. So if you have any questions that you're coming across, feel free to hang around and ask. Otherwise,